Here is the quiz. And here's the results. And everybody did this right, so sloppy looking red dot. So there we have a grid. And a curve. Starting from x equals -4, how far do we have to go before the value of y doubles? How far do we have to go on the x-axis before we get to a point where y is twice as great as it is here? You're waving, or is that? Okay. 4 units. Why is that? Well, because each of these lines is twice as close to the x-axis as the one before it. So as we go from the x-axis up to this line, it's twice as close as this one, which means this line's twice as far as this one, right? And then this line's twice as far as this one, this line's twice as far as this one, this line's twice as far as this one. And it doesn't matter what our values of y are. Y can have any value. But our doubling time is 4 units. Does that make sense? So I'm going to say regardless of the y values, and of course, provided that the red dot isn't y equals 0, because if it isn't, I'm going to say isn't true. We'd say that y doubles every time x increases by 4, okay? Then we'll say doubling time is 4 of whatever the x units are. Now, often we call it a doubling time because very often with exponential functions, instead of x, we're going to use t for time. Okay, a lot of exponential functions are functions of time. For example, the value of an investment or the value of, let's say, a bank account that has a constant interest rate. Any exponential function has this shape. And that shape can actually be extended. We could draw another line. We've got these vertical lines equally spaced. We could draw another vertical line at the same spacing and go up twice as high as this. We'd be up about here. Okay. We could continue going to the left. We could draw another line, vertical line to the left, and go half as high as this. Now, both ways, if we keep drawing vertical lines here and going twice as high, It's not gonna take long till we're out of the atmosphere. Okay? You know, we'd be up here, and then we'd be up close to the ceiling, then we'd be up close to the roof. Then it would be twice as high as the building. Okay, so you can see how the exponential function gets out of hand. If we go to the left, we keep going twice as close to the y-axis. How many times could you go twice as close to the y-axis as this until you can't tell whether you're in the y-axis or not? Okay, you go twice as close, you're here. 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 Another time, and I don't even know if I'm on the y-axis or not. At least not from the point. Now, theoretically, I'm not, because we can go twice as close as many times as we want. Okay? So those are important properties of exponential functions. Okay, well, this function has a formula y equals ab to the x. For the right values of a and b. Now, where are the x and y axes on this graph? Everybody made a really good graph. It's pretty clear. The y-axis is where x equals 0. Well, right here is your line x equals 0. So this would be your y-axis. And the x-axis is line y equals 0. So this is your x-axis. We can determine the values of a and b if we just know the coordinates of 2 points on the graph. Now we could actually, since we know the y-intercept, we can figure out the value of a very, very quickly, but I'm not going to do that right now. I'm going to do 2 points. I'm going to take this point where x equals -4. Let's take this point, -4, 1/2. And then let's take this point, 8, 4. I can say if y equals ab to the x, then, well, y is equal to 1/2 when x equals -4, right? So I could substitute y equals 1/2 and x equals -4 into this formula, into this, we call this the form of the function. Okay, so we have 1/2 equals a times b to the -4. Now, can you solve this equation for a or for b? Well, you can't figure out what a and b are just from this one equation. You have two unknowns in the equation, a and b. You need a second equation. Remember when we did this with linear functions, you got y equals mx plus b, you can plug in your y and your x values for one point, and then for another point, and you can figure out what m and b are. You can figure out the values of m and b. Well, I've got 2 points here. With 2 points, I should be able to get 2 equations that I can then solve for a and b. So the second equation tells me that y is 4 when x is 8. So here are 2 equations that I should be able to solve to determine the equation of this function. Does that make sense? So let's go ahead and solve. I'm going to ask you to solve. So I'll just keep this board at least visible over here. So you can refer to it, but I'll rewrite the equations. And you know what I'm going to do right from the beginning? Before I get too far in it. Since we usually want the variable that we're solving for to be on the left-hand side of the equal sign, that doesn't have to be there. You can do the operations no matter which side it's on, but we usually see things better. We're more used to seeing it on the left side. So I'm gonna switch the sides of this each equation. We got a b to the -4th equals 1/2, and a b to the 8th equals 4. Okay. Now, how are we going to solve this system of equations? Does anybody have a suggestion? Let's just say we wanted to find the equation of a straight line through these 2 points. Now, we're not going to find the slope and then plug in and find the intercept because we don't have a slope to find for this. We're going to do something that logically has similar steps to what we would do with the exponential function. I'll explain as we go. So let's say we have the same points, okay? -4, 1/2, and 8, 4. We can write (1/2) equals m times -4 plus b. In other words, we can plug -4 in for x and 1/2 for y. Remember doing that? And we could also write 4 equals m times 8 plus b. Now, what we could do, we could solve the first equation for b. And then we could plug that value of b in to the second equation. And we wouldn't have b anymore. Because when we solve for b, the expression we get just has m as a variable. No, I can solve that. You're going to get. So b equals 1/2 plus 4m. I mean, m times -4 is -4m. We're going to add 4m to both sides, and this is what we're going to get. And we plug this expression in for b here. And now we have an equation with just m's, and we can solve it. We also solve this equation by elimination. Here, we can't solve by elimination. We got to use a slightly different strategy. Let's solve one equation for A or B and plug that into the other equation. And that would be fine, okay? I'm saying it's less algebraically challenging to divide one equation by the other. That will eliminate a variable, just as solving this equation for B and plugging in here would eliminate the B variable and allow us to solve for M. And then, of course, once we solve for M, we can plug that into either equation and solve for B. So we're going to do that. I'll number these equations 1 and 2. Now, when I say divide one equation by the other, that's a shorthand for saying divide the left hand by the left hand and divide the right hand by the right hand. That's what I mean by is divide one equation by the other. You have to divide the left-hand sides, you have to divide the right-hand sides. What we get is AB to the 8th over AB to the -4th. Well, that's left-hand side divided by left-hand side. That equals 4 divided by 1/2. Okay, let me ask you if you can simplify this equation and see what happens. If you just simplify this side and simplify this side, let's see what you get. There's a little algebra involved here that you might be a little rusty with. I want to see what you need to, want to see what I need to tell you. Okay, people have a little trouble getting started here. It's okay. Figured I'd have to give some hints. First, 4 divided by 1/2 is 4 times 2 over 1. When you divide by a fraction, you multiply by the reciprocal. Everybody pretty much knew that. Of course, you want to write out that step to make sure you reinforce that, because you might forget it later in a more complicated problem. So you'd want to write out this step. Also, a times b to the 8th over a times b to the -4th is the same thing as a divided by a, which is very convenient because a divided by a is just 1, multiplied by b to the 8th over b to the -4th. Make sure we understand why that's so. If I multiply two fractions, I multiply the numerators. A times b to the 8th is ab to the 8th. So if I multiply this out, I get this numerator. And if I multiply the denominators, I get this denominator. So we can always separate it like this. Okay. So what's going to happen in the next step? Well, I think you know, because everybody, kind of knew what to do on the right-hand side. you get 8. On the left-hand side, you get 1. You might have gonna write it out. You get b to the 8th divided by b to the negative 4th. Well, we're kind of out of room here, so we'll come up here. We got b to the 8th divided by b to the negative 4th equals 8. Now, I've told you that you generally, when you have a denominator in an equation, you want to multiply both sides by the denominator. So you might have an impulse to do that here if you've been listening to me. But that's a hard thing for people to grasp sometimes. But we're not going to do that here because then you'd end up with b's on both sides of the equation. We've already got all our b's on the left-hand side. We want to keep them there. Okay, so what are we going to do here? Well, we're going to apply the rules for exponents. When you divide some number to one power by the same number to another power, you can subtract the exponents. You get that same number to the difference of the exponents, okay? So b to the 8th divided by b to the negative 4th is b to the 8th minus negative 4, which means you get b to the 12th equal to 8. Now, you're not going to figure that out on paper. You're not going to figure that out in your head, what power of b equals 8, okay? I know the third power of 2 is 8. So if we took the fourth power of 2, we would have the 12th, or the fourth power is, find the number whose fourth power is 2, okay? And that's like 1.14, something like that. So I think we're going to come out with something like 1.14, but that's just an estimate. To solve it, we have b to the 12th to the 1/12 equals 8 to the 1/12. Now, why does that help solving for b? It's because of the other rule for exponents. You take a power of a power, you multiply the powers. So this is b to the 12 times 1/12 equals 8 to the 1/12. 12 times 12 is 1, b to the 1 equals 8 to the 1/12. So b equals 8 to the 1/12. And I'm going to actually approximate that. I don't want to do the fourth root of 2. Actually, it's about, I think it's closer to 1.2 than it is to 1.21. No, actually, it's a little less than 1.2. I'm going to say 1.18 or 1.19. I'll say 1.19. Now let's assume that's correct. You can take your calculator and figure out whether it's correct or not. Okay. Yeah, if you want to do that, go ahead. I don't think it's much less than 1.18. I know it's less than 1.2. Whether you understand or you know, you might be rusty with rules for exponents. I'm going to write them down in a minute. but we see that we use the rules for exponents. And the rules that we use here are when you divide a number to one power by the same number to another power, you get that number to the difference of the two powers. You subtract the power of the denominator from the power of the numerator. When you take a power of a power, you multiply powers. Those are the two rules for exponents that we've used here. Okay, once we have b equals 1.19, you can plug b equals 1.19 into either equation. Choosing the first equation, use equation 1. Now I don't want to do the negative power of 1.19. I could, but using equation 2, you get a times 1.19 to the 8th equals 4. This gives you a times 8. I'll say approximately equal to 4. Turns out it's exactly equal. And you get a equals 1/2. So what we've done is we've taken these two equations, we've divided one by the other, which eliminates a. See, a got eliminated right here. Gave you an equation for b. We solved that, we got something like 1.19. We plug that back into the equation, either equation, but I chose to use equation 2. It's ab to the 8th equals 4. B is 1.19. We plug that in for b, and we get a times 1.19 to the 8th equals 4. 1.19 to the 8th is, I think, pretty close to 8. It's exactly equal to 8 if I have the right estimate here, but we won't worry about that. It's approximately equal to 8, so 8 times 8 is 4, so a is 4 over 8, which is 1/2, which tells us that y equals ab to the x becomes y equals 1/2 times 1.19 to the x. Well, you want to be able to use that process. It's going to come up in your homework. Okay. Now let me encapsulate the rules for exponents real quickly. See what I just wrote there? X squared times x cubed means x times x multiplied by x times x times x, right? I mean, that's what x squared means. That's what x cubed means. That gave us x to the fifth. Well, 5 is 2 plus 3. You see where the 2 comes from because we got 2 x's here. You see where the 3 is. We got 3 x's here, right? So if we got 2 x's here and 3 x's here, we're going to get 5 x's here. And if we got a x's here and b x's here, we get x to the a plus b. This is just, algebra 1. But it's probably been a while, so I want to make sure we review it. Well, this is one of the rules for exponents, and I used it. Well, I didn't actually use it. Here's what we can do if we're dividing. Okay, x to the fifth over x squared, 5 of them up here, 2 of them down here. We can divide these 2 by these 2 and leave these 3 and put a 1 in the denominator just to make sure we got our fraction lined up. And this equals 1, so that just leaves us x times x times x or x cubed. So it looks like x to the a over x to the b equals x to the a minus b. We do x squared cubed. That means 3 groups of 2 x's. An x squared here, an x squared here, and x squared here. That's x to the 6th. And if you think about it, we can generalize that. Say that x to the a to the b equals x to the a times b. What's x to the a divided by x to the a? Well, 2 answers. It equals 1 because you're dividing something by itself. By this rule, this is x to the a minus a, which is x to the 0. Well, x to the 0 equals this, and 1 equals this. X to 0 has to equal 1 then for any x. Another one. I'll write it this way, x to the 0 over x to the a is x to the 0 minus a, which is x to the negative a. But x to 0 over x to the a equals 1 over x to the a. So 1 over x to the a is equal to the same thing that x to the negative a is equal to. So 1 over x to the a has to equal x to the negative a. Okay? In other words, this is equal to this, and this is equal to the same thing. So this has to equal this. So we can say that x to the negative a equals 1 over x to the a. So there are most of the rules of exponents, the ones at least that we're going to need to deal with exponential functions. So you want to kind of review those and make sure you understand them. And you'll see them used in examples in the open math materials and elsewhere. And if you need more practice with them, I can easily give you a reference, but you just go to any chat, you can probably just put it into the address box of your browser and say, explain the laws of exponents. What are the rules of exponents? Explain that one to me. Give me an example. Ask me a question. It's not going to be good. If you say, ask me a question, or if you say, can you solve this? It's probably going to screw up. Okay? It doesn't do arithmetic well. It does higher mathematics very well. There's no arithmetic involved in higher mathematics. Okay? So you get to research level mathematics, and it's probably going to give you a good explanation. Give you an example. 18 months ago, I asked AI to draw me some linear equations of the form A times the quantity X plus B equals C, where A, B, and C are various numbers. He gave me a dozen equations and then the solutions. Gave me a dozen really good equations, they were all different. Gave me a bunch of solutions, they were all different. None of the solutions matched the equations. Okay, it just made up solutions. It gave me really good explanation that I might just post of how to graph a quadratic function. Okay. And then I said, okay, graph this function. I think it was really simple. It might have been like 2 times x minus 3 squared plus 6. That isn't what it was. Well, that's in vertex form. Okay, I might have given it one in general form, but this is vertex form. You know the axis of symmetry is x equals 3. That's the axis of symmetry. If you plug x equals 3 into this, you get y equals 6. Right there's your vertex, and here's your axis of symmetry. Okay. It showed me a graph. It had this point labeled as a vertex. And the graph was like over here. Okay. So it showed me a graph and it showed me a vertex. The vertex at least was on the axis of symmetry. It got that part right. Okay, but it didn't get the right coordinate of the vertex because it didn't know what the heck it was doing. It's just trying to put words together. Okay, and it's really good at it. It can convince you that it's really pretty smart, but it isn't. So you can't trust it. Now, when I say ask it to give you some exercises and rules of exponents, that's great. Okay. You go to a free online test. You want to do that? And give you instructions for finding a good algebra text where you do these things in detail. You might even be able to find it in open math. The open math usually doesn't go to the much below the level of a pre-calculus class. It doesn't go back to early algebra or pre-algebra very well. Just that's not what people are writing problems for. At least weren't last time I looked for them. That's not been that long. Okay, so you got to have the laws of exponents, but there they are. There are the rules. So hopefully you've kind of copied them down, but I'm going to quote them when I need them. The equation that the function that we graphed when we relabeled the graph and everything, okay, turned out to be approximately y equals 2 times 1.19 to the x. We could also write that as y equals 1/2 times 2 to the kx. All right? Just find the right number k here, and it works. Let me show you how that works. I'm going to show you that this could be the same as this. Okay, if y equals this and y equals this, then this equals this. That clear? Makes sense? So I can say if this is true, then the kx has to equal 1.19 to the x. I got 1/2 here and 1/2 here. I multiply both sides by 2, and I get this. Two to the kx. 2 to the kx is the same as 2 to the k to the x. That's one of the rules for exponents. It look familiar? It look okay? Comfortable with that? 2 to the k to the x, 1.19 to the x. Well, if 2 to the k to the x equals 1.19 to the x, two to the k equals 1.19. Now your formal algebraic step would be to take both sides here to the 1 over x power. Because 1.19 to the x to the 1 over x, a power of a power, you multiply the powers, x times 1 over x, 2 to the k to the x to the 1 over x is 2 to the k to the x times 1 over x. And x times 1 over x is 1. Two to the k to the first power is 1.19 to the first power, and that's just this. That's an application of laws of exponents. You want to maybe think through that one to get a little more familiar with it if it's looks unfamiliar, and it might well if it's been a while since you did a lot with exponents. Okay. Solve for k. That you don't know how to do, but you will when we get to the end of chapter 4 in about 2 weeks. Okay. It's easy once you know how. I'll just tell you the solution is then that k is base 2 log 1.19. Which is approximately 1/3. But the log 2 function is the inverse of the 2 to the x function. Swap variables in the 2 to the x function, you get the log base 2 function. I'm just telling you that as a preview. You don't have to remember it. But think about it long enough to write it down and say, yeah, kind of remember this. So when we actually do it, you'll have a context for it. Okay. Y equals 2 to the x. The y-axis on the y equals 1 line because 2 to the 0 equals 1, right? And we know that already because we made the tables early in the semester and we talked about that much about the rules of exponents. Okay. And when x equals 1, lo and behold, y equals 2. And when x equals -1, y equals 1/2. So there are 3 points on this graph, so we can just make our exponential curve there, and we see then that we have a graph of y equals 2 to the x. You get a prettier graph and a more accurate graph if you subdivide your rectangle. But right now we're going to worry about the numbers and not so much about the rectangle, okay? Not so much about the window. So we want to graph other functions like, how about y equals 1/2 to the x? Well, when x equals 0, we get 1/2 to the 0, which means we go through this point, okay? When x equals 1, 1/2 to the 1 is 1/2. So we're going to have a point over here. When x equals -1, 1/2 to the -1 is 1 divided by 1/2, like the rule says. Yeah, you've seen the rule. I mean, we used it a month ago, 2 months ago. So we have these 3 points, and your exponential function looks like this. That's a decreasing exponential function. Now, an increasing exponential function we could use to model a population of fish in a pond. You got an empty pond with plenty of food in it. You throw in a few fish and they grow exponentially, they reproduce. The more fish you got, the more new fish you get. The more fish you got, the more eggs are laid, the more hatch out. And if the pond is big enough, most of the ones that hatch out don't get eaten, okay? Or at least the same percent of the ones that hatch out don't get eaten. Well, that would be an increasing exponential function, just like a investment at constant interest rate. Okay, this 1.19 to the x. Let's say you put $500,000 in at 19% interest. Okay, now you probably don't have $500,000. Neither do I, but you invest $500,000 at 19%, and that's how your money's going to grow. Okay. You might find somebody that gives you 19%, but it would be a high risk investment. They're invested in some bubble and they're anticipating the bubble will continue to grow. And if it does, everybody's going to be happy and everybody invests with them is going to be happy. If not, they're going to go broke, so they're not going to have to give you any money back. Okay. They're going to go bankrupt. They won't have the money. So you're risking your investment if you look for 19%. But of course, a 19% interest would double in less than 4 years. So your money would grow really fast. Okay. All I'm saying is that graph that you labeled could model $500,000 invested at 19% interest, and it would go like that. And at the end of 8 years, you can see you'd have about $2 million when, which isn't bad. As far as, the growth of the investment. And if you have, well, I won't go any further. Okay, this could model radioactive decay. Radioactive elements decay. Some of them decay faster than others. Just looking at the time. Okay. Well, that's 2 to the x. That's 1/2 to the x. What if we wanted to do 3 to the x? What would be different? What would you do with this graph to make 3 to the x? Well, if we want to do y equals 3 to the x, I'll put that in a different color. We can just look at the value at -1, 0, and 1, and we get a real good picture of the function. If x is 1, then 3 to the x is 3. If x is 0, y is 1. And if x is -1, y is 1/3, which is just a little less than 1/2. Now, I'm not going to try to put 1/3 in there, but you could calculate it. There's not enough room there to really label anything. But you see that this graph is going to be lower than the 2 to the x graph until we get to 0, and then it's going to be higher. Fair enough? That makes perfectly good sense. Still has the shape of an exponential graph. If you take the exponential curve that you construct, that you learn to construct on the first day, take that exponential curve and let's say that's the exponential curve you construct on the first day. Well, you just squeeze it in a little bit and you get this exponential curve. Stretch it out a little bit and you get a much more gradual exponential. It's going to have exactly the same shape, but stretched out or compressed. Y equals 1/3 to the x, you can work out, but 1/3 to the -1 is 1 divided by 1/3, which is 1 times 3/1, which is 3. So it's going to be here. It's going to be at 0, of course, and then it's going to be down to 1/3 here, and the graph would look something like this. Be like, this is radioactive decay, one element, this is radioactive decay of another element that decays a little faster. Or one of these curves could model the amount of some medication in your body. Okay, you take a medication. If you read about the characteristics of a medication, it will tell you the half-life. Okay, tell you how long it takes it before you have half as much. Typical half-lives could be anywhere from 4 hours to 16 hours. Those would be typical. Some of them might be shorter, some of them might be longer. Basically, those things are filtered out of your body and excreted, okay? And if you're taking multiple doses of a drug, and you got a drug with a half-life of that much, so it drops to half between here and here, or say between here and here. Okay, then you take another dose of the same size. Well, that dose is added to what's already in your bloodstream, so you go up to here and you fall back. Okay, and you take another dose and it goes a little higher, but it reaches a limit. That's why they tell you to take your doses regularly. If you miss a dose, don't take an extra one. Just get your next one. And it gets that medication up to a maintenance level, which is where you want to be. And it gets pretty close to maintenance level after just a couple of doses. Grows more and more slowly toward the maintenance level. That's very interesting, okay? And one thing, one of the assignments you're going to have for the weekend is, well, there are 2 assignments. One is graphs of exponential functions. You've already got a good background for that. And you're going to see graphs like this. And another is just a series of problems that give you the exponential function and ask you to calculate things with it. Okay, gives you a number of good examples. See how much time we've got. Yeah, we've only got 2 minutes, so I've laid a lot of stuff on you. So I'm not gonna rush and try to do any more examples, but exponential functions are really powerful, maybe the most important functions in the universe, because you do exponential functions and plug complex arguments into them, and you can get sine and cosine functions and vibrations and oscillations and all that stuff, but we don't do that. It's well beyond a free calculus level. y equals 2 to the x, the inverse function is y equals log base 2 of x. And there is one more thing that I intended to tell you, so I'm going to tell you real quick. Y equals e to the x. There's a definition of e. And it's approximately equal to 2.7. So where would a graph of e to the x be on this picture? Well, if e is about 2.7, then this would be between the graph of 2 to the x and the graph of 3 to the x. 2.7 to the x would be between 2 to the x and 3 to the x, closer to 3 to the x, right? It makes sense? E is also a number on your calculator. You got an e to the x button on your calculator. You want to raise e to the power, you just do it in your calculator. You don't have to do that in some of the problems in section 1. Okay, so the graph of e to the x is in here. It turns out that the slope of the graph of e to the x is just equal to e to the x. Okay? You plug in x, it'll give you y coordinate of the graph. And if you do the slope of the graph at that point, it's the same. Which is really kind of neat. When you get to calculus, that becomes a really important and a really kind of a nice thing. It's real easy to do derivatives with the exponential function. Anyhow, enough is enough. So I was going to let you go early. Now we're over about a minute, but okay. Have a good weekend. Email me if you have questions. If you email me tomorrow, don't expect a response until Saturday because I'll be out of town for a day.